Hello, we're going to cover section 2.2 on about comparing sets. So I'm going to start by giving a few definitions. And the first one is when two sets are equal. So this is on page 52. Two sets A and B are equal if they have exactly the same members. In this case, we write A equals B. If A and B are not equal, we write A does not equal B. And when we are comparing sets for equality, repetition of elements and order are not important to determine whether two sets are equal. As long as the elements are the same. Okay, in the first example, they are asking us which pairs of sets are equal. That is, they have whether they have the same members. So all this is from page 52. Okay, first question, which pairs of sets are equal? The first set is Facebook, Flickr, Twitter, Pinterest, Instagram, and TikTok. And the second set is Pinterest, Flickr, Instagram, Twitter, Facebook, TikTok, Flickr, and Pinterest. And the sets are equal. They have the same elements. Just because a few elements or just because a few members are repeated or in different order, that doesn't make the sets different. So the sets are equal. In part A, the sets are equal. Neither the order nor the repetition of elements matter. And B, we have two sets. Set A, the set of all X, such that X is a citizen of the United States, and set B is the set of all Y, such that Y was born in the United States. So in B, the sets are not equal because there are many ways to obtain American citizenship, not necessarily by being born in the United States. So the sets are not equal. For example, we can think of celebrities who were born somewhere else but were citizens, like Ryan Reynolds, Sofia Vergara, Natalie Portman. The book gives us an example, Arnold Schwarzenegger, but those are a few. So I'll try to type this. So Arnold Schwarzenegger. Were born, well, are citizens, are American citizens who were not born in the United States. So for sets to be equal, they must have the same elements, regardless of repetition or the order in which they are written. So two sets are equal if they have the same members, and they are equivalent. Two sets are equivalent if they have the same number of elements. So equal and equivalent are not the same thing. That's still page 52, so I'm not going to write down the page number. So sets A and B are equivalent, or in one-to-one correspondence, if the number of elements of A equals the number of elements of B. Another way of saying this is that two sets are equivalent if they have the same number of elements. So in example 2, we will determine whether the sets are equal or equivalent. This is on page 53. And if two sets are equal, well, they will automatically be equivalent. Okay, so set A has elements A, B, C, and D. And the second set has elements D, B, A, C, D, and C. So the sets are equal. Sets are equal. And if they are equal, they are equivalent. So some of the elements are repeated, but they have the same number of elements. And part B, the sets are not equal because the elements are different, and it only takes one element for sets to be different, like 1, 2, 3, and 4, 5, 6, but they have the same number of elements. So the sets are equivalent. Sets are not equal, but they are equivalent. The next type of relation is a subset. Whether a set is a subset of another set. That's still on page 53. The set A is a subset of the set B if every element of A is also an element of B. We indicate this relationship by writing A is a subset of B. Otherwise, we're going to cross it. So the notation is A. This stands for A is a subset of B. And if you cross it, this do indicate that A is not a subset of B. So here's another example. Example 3. We are going to determine whether one a subset, whether one set is a subset of another set. Okay, so we have to say, and by the way, it takes one different element for sets not to be equal. So in A, we need to determine whether set A, consisting of 1, 2, 3, is a subset of B, which consists of 1, 2, 3, 4, or the other way around. And the answer is yes. Every element of A is an element of B, but not the other way around. So A is a subset of B, but B is not a subset of A. And B, they give us this set of factors: Viola Davis, Peter Dinklage, Neil Patrick Harris, and Julia Louis-Dreyfus, and the set of all X, such that X has one anemone. Well, if you don't watch a lot of TV, that's okay. But just wanted to tell you that A is a subset of B. So these four actors, they have one MS. So A is a subset of E. But E is not a subset of A. And we can think of many actors who won MS other than these four. Like, for example, let's say Dick Van Dyke has won MS, but is not in set A. But is not a member of set A. So as a note, I'll have to, I cannot write the set terminology. But if A is a subset of B and B is a subset of A, then A and B are equal. Then A equals B. We can always draw pictures to represent sets by using Venn diagrams. So an effective problem-solving technique for working with sets is to draw pictures called Venn diagrams. So on the left, we can see this Venn diagram that illustrates that A is a subset of B. We represent the universal set by a rectangular region labeled U, the region labeled A, and sets are going to be denoted by circles or ellipses. So the region labeled A is completely contained in region B, indicating that all of A's elements are also in B. Most times when we say that A is a subset of B, there will be some elements of B that are not elements of A. So we can formalize this idea with in the definition of a proper set, but in a Venn diagram, we will represent the universal set with a rectangle. And we can have different situations. So we're going to have a rectangle that represents the universal set. One situation could be set A containing set B. And this is to denote that A is a subset of B. Now, there are other situations, but that's just one. I will keep working with Venn diagrams with more details in section 2.3. Okay, so we talked about subsets. And we also have proper subsets. The set A is a proper subset of the set B if A is a subset of B, but A does not equal B. We write this, the notation is similar, except that we don't have a bar at the bottom. If A is not a proper subset of B, we write that A, well, we cross the symbol. Okay, so let's write a note. If you cross the symbol, that's to indicate that A is a subset of B, and the sets might be equal. So we don't know everything, but sets might be equal. With proper subsets, the sets cannot be equal. So A, this symbol or this notation is used to indicate that A is a proper subset of B. So A is a subset of B, but they are not equal sets. Okay, so we're going to decide whether each statement is true or false. Those are on page 57. Number 10. We have two sets. And remember that repetition of elements and order is not important when determining whether sets are equal. So we have a list of dog breeds. Those are Collie, Poodle, Beagle, Chihuahua, and Bulldog. And the other set is Bulldog, Chihuahua, Beagle, Poodle, and Collie. So both sets have the same elements, but they are in different order. So the answer is true. This relationship is true. And in fact, sets are equal. So it is true. However, they are not proper subsets of each other because the sets are equal. And number 12. Okay, so we're going to think of capital letters and lowercase letters as the same thing. So capitals and lowercase, we're going to treat them the same. They are asking us whether these sets are proper subsets of each other. The first set is the set of all t such that t is a letter in the word root. And the second set is the set of all z such that z is a letter in the word root. Oh, by the way, the t is just set notation. I mean, it's not the t, it's not the same t as the letter in the word root. I mean, we know that z is not a letter in the word truth, is just set builder notation. So repetition of elements doesn't matter. And if we treat capitals the same, if we treat capital letters the same, we have that the sets at the end are equal. So this is false because the sets are equal. They are going to be subsets of each other, but they are not proper subsets of each other. The next exercise is to find all subsets of a set. Okay, so I'm looking at this part. Yeah, at the subsets of a set. Okay, so we did that. They are asking, so I'm not going to do that one. Okay, they don't, the book doesn't say a lot about that. So I'm just going to do this exercise by hand on finding subsets. So we're going to find all subsets of the set A, B, C, D. We're going to organize this information on a table by the size of the subset, the subsets of this size, and the number of subsets of this size. Okay, so the subset ABCD has 4 elements. That means every subset will have either 0 or 1 or 2 or 3 or 4 elements. So those are the possible sizes of the subsets. And there's only one subset of size 0, and that's going to be the empty set. So the empty set is going to be a subset of everything, even itself. Subsets of size 1, there are going to be 4. The set with the element A, set of the element B, C, and D. Okay, I may need more space to write the next one. So there were 4 elements or 4 subsets of size 1. Now subsets of size 2 that are going to be there are going to be 6. Those are AB, AC, and AD. We know that at this point we know that repetition doesn't matter. So AB is the same as BA, and BB is the same as B. So the next one is BC and BD. So BC and BD. So CI is the same as AC, CB is the same as BC, CC is the same as C. The last one is CD. And we already included everything with D. DA is the same as AD, DB is the same as BD, and DC is the same as CD. So there are 6 elements of size 2. Subsets of size 3. So we can start with ABC and remove 1 element. Those are good. There are going to be 4. If you remove D, you have ABC. If you remove C, we have ABD. If we remove B, we have ACD. And if we remove A, we have BCD. So that's going to be 4. So I'm trying to make this visible. So that's BCD. And there's only one set of size 4, which is going to be itself, the set itself, ABCD. Okay, so add the numbers of subsets. 1 plus 4 plus 6 plus 4 plus 1 is going to be 16. So the set has 16 subsets. And we listed them all. So the set ABCD has 16 subsets. And there's a formula for the number of subsets of a set, depending on the number of elements of the set. That's on page 56. The number, so a set that has k elements has 2 to the k subsets. So in the last example, the set that we began with had 4 elements. So the set has 4 elements and 2 to the 4th subsets. I'm going to talk about the exponents later on, but an exponent indicates repeated multiplication. So 2 to the 4th is to multiply 4 times. In the last example, if we have, especially if we have a small number of elements, we can count subsets by drawing a tree. Okay, so we are going to draw a tree to count the number of subsets of the set, red, blue. Okay, so that set has 2 elements and it's going to have 4 subsets. 2 times 2, 2 squared, 2 times 2 is going to be 4, so it's going to have 4 subsets. So with a diagram, we have a beginning point. We can determine whether we choose red and whether we choose blue. Okay, so the first two choices is that the subset may or may not have red. And it may or may not have blue. So it may have red and blue, or red but not blue, or not red but have blue, and none of those. So we have four subsets as expected, and at the end the sets are going to be red, blue, red, blue, and if it doesn't have any elements, it's going to be the empty set. So this is it. Thank you for listening.